Alright, hello to CHEM and EASC 322. My name is Paige, and the pharmaceutical I chose for my project is cyclophosphamide. So what is cyclophosphamide? Cyclophosphamide is an antineoplastic drug. Antineoplastic drugs are most commonly used to treat cancer, so you've probably heard of them referred to as chemotherapy. It's used to treat breast cancer and ovarian cancer, but it's also used to treat other diseases like lupus and a few other different types of illnesses. How it works is it rapidly kills dividing cancerous cells, but it also targets healthy cells, and it kills these cells by interfering with their DNA synthesis. It comes in a few different forms. You can get it in liquid, like injections, or people also take them as pills as well. The environmental effects of cyclophosphamide are generally under-researched. We do know they enter waterways, and we've detected concentrations of them, but pharmaceutical pollution tends to focus more on antibiotics, anti-inflammatories, and antidepressants as a sort of topic of focus. The popular use of cyclophosphamide means a lot tends to enter the environments. It's one of the more popular antineoplastics. It's pretty commonly used, which results in pretty large amounts entering the environment. One example is this case study from Frank-Griel, which we'll look at later. So they looked at watersheds in Spain from 2010 to 2015, and they found that in 2015 alone, there were 23.4 tons of antineoplastics consumed in Spain, so that does include cyclophosphamide. Entry into the environment. So how it gets into the environment is released via hospital and urban wastewaters. Hospital wastewaters are not treated in-house, so they just enter into the sewage system and are later treated at water treatment plants. How they get into wastewater is their transformation products, and also cyclophosphamide itself is released via excretions from patients who are taking chemotherapy. The amounts released do vary from country to country. That's mostly due to, obviously there's differences in the proportion of cyclophosphamide that's consumed in countries depending on how they tend to treat chemotherapy or on how their wastewater treatment plants work. In Portugal, they found it to be a moderate to low risk based on environmental concentration, but acute levels have been found to have long-term effects, and that's due to the direct and indirect interference with DNA that cyclophosphamide has. So this case study, this is one that was done on Spain on a variety of watersheds from 2010 to 2015. In Spain, they found that more than 90% of urban wastewater is treated, and the main modes of treatment are degradation and sludge. This investigation looked at consumption of 78 anti-cancer drugs from 2010 to 2015, and that was in Spain. So that included cyclophosphamide, which was in the L01 antineoplastics category. They found that generally there were pretty high concentrations in urban areas. Consumption did vary temporally, so as you can see in 2010 there's a higher proportion of antineoplastics consumed than in later years, and that was mostly just due to changes in popular treatment. So that would likely be a trend in other countries as well, depending on what modes of chemotherapy are most widely accepted. So here, this is the fraction of cyclophosphamide that's excreted. So that's 25% of cyclophosphamide is excreted by patients. This is the fraction removed by wastewater treatment, so 0, which is obviously less than ideal. So then this is the consumption per day over the span of this experiment. It was highest in 2010, then it stayed pretty constant from 2011 through 2015, around that 70 mark. This is the predicted environmental concentrations in effluent. So we had 3.1, 2.8, 2.9, again staying pretty constant, and same thing for predicted environmental concentrations in the rivers that they looked at as well. Alright, so reactions in water. The hydrolysis reactions are pretty much the biggest thing that we have to worry about. And they did find that they are pH and temperature dependent. So at 20 degrees Celsius, between pH of 1.2 and 3.4, they found that hydrochlorides are produced. And here, breakdown is rapid with a half-life of 1.4 days. Then from pH 3.4 to 8.6, there's minimal cyclophosphamide degradation. The only exception is from 5.4 to 8.6. There is production of this 9-member ring compound, which I did try to find a name for, but the authors just called it unknown 9-member ring compound. So this is produced in pretty minimal amounts. And just to put these pHs into reference, EPCOR likes to maintain their wastewater an average of a pH of 7.6. So that's within this range where there is some of this 9-member ring compound produced, but it's at pretty minimal levels. So it's mostly cyclophosphamide that's going to be present in wastewaters, at least those treated by EPCOR. So next we have reactions at 37 degrees Celsius. So at pH 7.4, again, they found that this ring was produced. Overall, they found that the hydrolysis products of cyclophosphamide are not toxic. It's mostly just that cyclophosphamide itself that persists that causes issues when it comes to the environment. And then over here is all the different pathways based on temperature and pH and the products, and then also the reactions of the products, but those aren't problematic. Reactions with bacteria. So this was a study done on E. coli. And what they were studying was the effects of cyclophosphamide when it's in the presence of vitamin C. And why that's relevant is a lot of patients who are taking chemotherapy are prescribed vitamin C, especially with cyclophosphamide. It mitigates some of the negative effects of chemotherapy, so it's pretty widely prescribed. And then vitamin C in general is one of the most common supplements taken. So it's a given when it comes to wastewater, so it's always going to be present in mixtures where cyclophosphamide is. So what the authors found is the strongest lone cytophosphamide toxicity occurred at 3.5 micrograms per liter, so that is this one here. And then toxicity was highest in mixtures when it was at 350 micrograms per liter. So that is over here, and these are all the mixtures. Low concentrations, they found that vitamin C weakened cytotoxicity of the cyclophosphamide. So we had low concentration... Oh. Yes. Low concentration, 3.5, toxicity here, pretty high. Add in the vitamin C, slightly lower. At high concentrations, the vitamin C enhanced cytotoxicity. So this was a concentration of 350 micrograms per liter, and then as soon as you add the vitamin C, it's a little bit higher there. So the authors mentioned in this paper as well that most of the cytotoxicity research done on cyclophosphamide focuses on it alone in solution. There's pretty little research into how it reacts in mixtures, so this research was done in 2020, so it's still an ongoing topic, trying to figure out what other co-contaminants can affect the toxicity of cyclophosphamide, so that's important to take note of. So, effects on ecosystems, lakes, rivers, and groundwater. So, in terms of biological effects, cyclophosphamide was found to be harmful to crustaceans. This was from a study done on Daphnia, which are a model organism when it comes to looking at crustaceans. It's also found to be cancerous in amphibians, so both those make it pretty troublesome to have cyclophosphamide in lakes and rivers, where both crustaceans and amphibians reside. It's also very mobile in soils. So this was a study done, again, on mixtures, and they found that alone, cyclophosphamide pretty rapidly enters groundwater. There's less leaching when it's in the presence of co-contaminants. In this study specifically, they used metoprolol, which is used to treat high blood pressure, chest pain, and a bunch of other cardiac-related illnesses. So they did find that there's less leaching because cyclophosphamide sorbs to the metoprolol. However, once it sorbs, it tends to be harder to remove from the environment. Alright, so for removal, the first method is UVB photolysis and chlorination. So in this study, they used UVB light. UVC also works, but UVB is more efficient and generally accessible when it comes to wastewater treatment. They found that this method is most effective at high cyclophosphamide concentrations and at lower pH. So they found that it resulted in 58% of cyclophosphamide becoming mineralized, which could then be removed from wastewater treatment. However, the products are toxic to fish. So they suggest that more research is needed to successfully remove both cyclophosphamide and transformation products, since the transformation products from these reactions were toxic to aquatic life. Then here's just some diagrams. So we can see the UV photolysis alone didn't really remove much. Same thing goes for chlorination alone. But then when you do the UVB photolysis and chlorination, it's pretty significantly reduced the concentration of cyclophosphamide. And then this is just showing that increased chlorine concentration increases the efficiency of cyclophosphamide removal by UVB photolysis and chlorination. Next, we have removal via ozonation. So what this experiment did is they bubbled ozone through solutions with pHs of 5.6, 9, and 11. They kept the ozone concentration between 0 and 0.6 milligrams per liter, and they found that generally this was most effective at pH of 11. So you can see that here. This was pH 11, most significant cyclophosphamide removal. The lower pHs, 5.6 and 9, were somewhat effective, maybe 50% at most after 30 minutes. And how this works is the hydroxyl radicals that are produced from the reaction of ozone and hydroxide ions attack cyclophosphamide and aid in breakdown. The biggest issue here was the residual total organic carbon, which was toxic. So again, it's effective at removing cyclophosphamide, but the byproducts are pretty toxic to aquatic life, so there's more research needed on more ideal removal methods. So, in summary, cyclophosphamide is a popular antineoplastic, so it has pretty plentiful release into the environment due to its popular use. It's been detected in the environment and is difficult to remove via wastewater treatment, like that example we saw from Frank Real in Spain, where 0% was removed. Low concentrations are toxic to aquatic life, and high concentrations are especially toxic when it comes to mixtures, so that's from that vitamin C example. Effects on the environment include harm to crustaceans, amphibians, and leaching into groundwater. And environmental effects and removal from wastewater need more research, as well as effects in mixture and other contaminants. So generally, we have a pretty solid basis of understanding of why and how cyclophosphamide is detrimental to aquatic environments, but we need a lot more research on interactions with other drugs when it comes to effluent. Here are my references. Thank you for watching, and I hope you enjoyed.